Hello, everyone. This is Professor DePaula. Welcome you back to Psych 220 Behavioral Statistics fully online. And in this week's chapter, we will be covering some basic probability theories and their interactions with z-scores. So our chapter 6 learning objectives include understanding the definition of probability, explaining the assumptions of random sampling, and how that differentiates itself from other forms of sampling that we may encounter in psychology. Using the unit normal table to find probabilities. This is the standard normal distribution table that you have in your appendix, and it's basically the normal curve that's been integrated and put into a tabular format. Using this unit normal table to find scores for given proportions. So this is basically the table of z-scores that we're talking about, and how to look up the table of z-scores and find the proportions or areas under the curve, and to find percentiles and percentile ranks in the normal distribution. So most of this chapter is going to deal with looking at the normal distribution table and using it to extrapolate information regarding probability, percentages, proportions, areas. They're all basically the name for the same thing. That occur underneath this curve. So everything in research involves probability. There are no facts. There are no laws within psychology. So this is not physics. This is not chemistry. This is not even biology, where things are kind of, I guess, taken for granted in some situations. In psychology, basically, there is no agreed upon norms or laws or truths. Everything's based on a hypothesis, and within a hypothesis, there's a probability that it's correct, and there's a probability that you've made an error with your hypothesis. And everything's based on probability. You cannot be 100% certain of anything. That sounds horrible, but that's the truth. So there is no guarantee that your idea is correct. Even if you run study after study after study and you get the same answers that you're looking for, there's a high probability that your hypothesis is supported, but you can never guarantee it being correct, and you can never guarantee it being wrong either. So hypotheses within psychology are probabilistic, right? So there's a high probability of it being supported versus a low probability of it being supported. That sounds kind of not science-ish, but it is, because we don't have any guarantees in psychology, because the things we measure are very difficult to measure. This is not measuring gravity, where we can all agree on something, or measuring weight, or measuring heights, or measuring speed. Trying to measure someone's level of anxiety is a guesswork, right? It's not 100% guaranteed to be accurate. But you can get things that are more likely and less likely, and hopefully your research gears towards more likely. Research is conducted using a sample. A sample is a subset of the population, and we try to draw an inference based on the sample, an inference about the population. So we're always going from sample to population, and that is the basis of inferential statistics. Relationships between samples and populations are defined in terms of probability. So if you know the population, then you can say something about the probability of obtaining a given sample from the population. The problem is, in psychology and most other fields, we don't know the population. We have to try to make a guess about the population based on the sample, and that's a lot harder than basically qualifying what the sample is going to look like if we have the population parameters. So probability is when we know the population and we can determine the probability of the sample. Inferential statistics is when we have the sample and we try to make a guess as to the parameters of the population. That's the tricky part, is we can be off. You can't really be off when you're talking about the values of a sample based on the population. You're going to be pretty much on track if the sample is big enough. So the sample will match the population when the sample is a big enough size. The problem with going from a sample to a population is, yes, a big sample will help try to make an inference about a population, but we cannot be certain because there's many possible samples that can be taken from a population, and some of those samples can represent the population better than some other samples. And in this chapter, we're going to be talking about the simple random sample, which is probably the best estimate of a population compared to all the samples that we can have. The problem with the simple random sample is in psychology, this is very unrealistic. We generally don't run simple random samples. We run something called convenience samples, which is basically we get whoever is available in our study. And whoever is available generally is not representative of the entire population we're looking to draw a conclusion about. And that's a huge issue. And that creates something called the replication problem, where someone supports a hypothesis, and then another group of researchers try to replicate or redo that study and come up with the same, support the same hypothesis, the same conclusions, draw the same conclusions, and they can't do it. And that becomes known as the replication problem, where one study finds an effect and the other study doesn't find the same effect, and then we don't know who's right and who's wrong. And unfortunately, in psychology, we need to do a better job at trying to come up with representative samples. The problem is that they're just very hard to get a representative sample of a given population. It takes a lot more work, a lot more money, and a lot more resources that we generally don't have to do this. Instead, we're back to the convenience sample, and we're back to whether that's representative of the population, and a lot of times it's not. And then it's back to replication, which then is inconsistent. So ideally, if you're using a convenience sample, you would want to replicate or redo the study with a different sample. The problem is most people just publish one study and they move on. And then if someone wants to challenge that study, you get a conflict. And we don't know who's right and who's wrong if they can't replicate. So let's put aside the whole business of sampling and replication temporarily, and let's talk about basic probability. When several outcomes are possible, the probability of a specific outcome is the proportion of all possible outcomes. So think of it as the number of successes over the number of outcomes. So whatever we're looking for, that's the number of successes. Every possible outcome is the denominator. Probability ranges between 0 and 1. If the probability of 0, an event is impossible, it cannot happen. If a probability is 1, that means it's certain to happen. That means it always happens. In psychology, though, we don't have to worry about 0 and 1. We're always in between those values. And unfortunately, we're kind of closer to 0 because a lot of the events, we're always testing the null hypothesis, and we're going to get into this later on in the course. But we want to basically, we're kind of doing it backwards. We're not talking about the probability of supporting our hypothesis. We're always talking about the probability of not supporting the opposite hypothesis, which is known as the null hypothesis. And when we get to hypothesis testing, this is going to make sense, but it's kind of a reverse way of thinking about testing our hypothesis. So little p is the symbol for probability. So you see p, and in parentheses the event. So whatever you're looking for is in those parentheses. For example, the probability of drawing a red ace from a standard deck of cards is the probability of a red ace. And probabilities are always given as decimals or proportions. The probability of a red ace, well, there's two red aces. There's the ace of diamonds and there's the ace of hearts. And there's 52 cards in the deck, so it's 2 over 52, which is 0.03846. That's your probability of getting a red ace in one draw of a card from 52 deck, standard playing card deck. A sample, and we're talking about a simple random sample here. A simple random sample is when every individual in the population has an equal chance of being selected. And the probability of being selected stays constant from one selection to the next. So this requires sampling with replacement. So if you're going to draw a simple random sample, you always have to draw it with replacement. That means if you select an object, you need to replace it so that the next time you draw, that you have the same probability of getting that object. For example, if I'm taking a sample and it involves the number of red aces, like in the previous example, if I get a red ace the first draw, I need to then put that red ace back into the deck. I need to replace it so that the probability is the same on the second draw, on the third draw, etc. Now, this is not realistic in research, like in psychology research, because we generally don't replace people. We don't want to count them twice. So if you're in the sample, we don't put you back into the group and select you again. You can only be selected once. So in our research in psychology, we sample without replacement, which means that the probability will change for each particular person you sample from the population. However, that's not really a problem because every individual in the population still has approximately an equal chance of being selected. If the population is very large, right, and I take one person out of that population, then the probability of selecting another person is going to be almost exactly the same as the first draw. So when the population is large enough, this idea of not replacing that object or that person back, putting that person back into the population, doesn't mean much because the probability is going to be almost the same. So think of the simple random sample as solely every individual in the population has an equal chance of being selected. So if I'm going to take a sample of psychology majors at BMCC, let's say I take a sample of 10 of them, and I draw from the list, there's probably 1,300, 1,400 psychology majors. If I take one person out of that group, there's still going to be 1,399 psychology members left if I took the number 1,400 out and put them in my sample. So the probability of selecting a person the second time is going to be almost exactly the same, because I've only removed one person, that it would be the first time. So this is not an issue. This is an issue if you have a very small population and then you take somebody out of the population before you select subsequent members of the population into your sample. Then it really changes the probability. But with a large enough population, this is not going to be an issue. And in psychology, our populations are super large, right? You're talking about populations of people that have depression. That's a ton of people in this country, if not the world. And let's just say in this country or in New York State even, that population of people with depression is gigantic. So if I'm sampling from that population and I remove 1 to 10 people, there's still thousands, if not more, hundreds of thousands of people that have depression. Maybe even up to millions of people that have depression in New York State. But that's how many people have depression. So unless I have a very limited population, withdrawing people and putting them in my sample is not going to affect the probability of subsequent draws from the population, and therefore, the number two stipulation that the probability stays constant from one selection to the next. This is okay with a large population. It might change ever so slightly, but it's basically the same. So you don't have to really worry about that if you're sampling without replacement. I know the book says sampling with replacement, but with a large enough population, it's not going to change much. So random sampling is important because if you take a random sample, you have the greatest chance of that sample being representative of the population. The problem is, if you're going to do a random sample, it's very difficult. So for instance, let's say I wanted to take a random sample of students at BMCC. Well, BMCC has 25,000 students. They go to school all hours of the day, on the weekend, and sometimes online as well, right? So to make sure that every member of the population has an equal chance of being in your sample, you would need to go find a list of those 25,000 students and then randomly assign numbers to them and draw them, or draw them out of a hat or a random number generator, and pick 100 people at random and then go find them. And some of them only go to school on the weekends, some of them only go to school at night, some of them go to school remotely, some of them are in another country that are studying at BMCC. So now if they're in your sample and they're in another country, you have to go to the other country to get them and administer your experiment or your survey. I guess you could do it online if you're doing surveys. But if you were to do an experiment, you got to get that person from out of country now to do your experiment. And you see that's going to be very resource intensive, which is why in psychology and many other behavioral sciences, a random sample, even though it's the best, most representative sample you can have, it's just not realistic. So instead, we use a convenience sample, and we get who we can get. Now, the convenience sample is not necessarily representative of the population, but if I replicate, that means if I do the study again with different people, and I replicate the study, even with a convenience sample, I'm pretty confident once I replicate. If I have a simple random sample, replication is not as important. But when I have a convenience sample, you have to replicate. Now, in psychology, unfortunately, people don't replicate. They don't have the time, they don't have the resources, and that's one of the drawbacks of psychology and other behavioral science fields, is the lack of replication. And then when they do replicate, they get different results, and that's a whole replication problem, and that's controversial. People don't know what that really means. It probably means that we have to replicate more. And I think one of the other reasons why people don't replicate is not only is it time and resource intensive to run another study again, you can't publish a replication. So journals are not interested in replications. And so why are you going to spend money and spend a lot of time replicating if journals are not interested in replications and you can't publish it? And you couple that with the publisher pressure mentality at all schools, including BMCC. There's still a publisher or parish. I mean, it's lower than, say, at Columbia, right? Where at Columbia you have to get X numbers of papers with a certain, index of citation indices and stuff like that, right? It has to be in certain journals. At BMCC, that's not the case, but you still have to publish. And so why do you want to waste months running a study, a replication that you can't publish? That's a big issue. So until psychology becomes more replication, publication friendly, right, you're going to have a lack of replications. We can display probability in a frequency distribution graph, like a histogram, showing the number of people or number of items within each value. Now, this is only effective if you have a very limited number of data in a population, and that's not going to work in real research. But for like a sample, for like an example like this, it's something that you can plot. So you look at the frequency graph, the histogram, and you could tell based on the histogram what the probability of getting a particular value is. And here's your frequency distribution histogram. Obviously, this is a very small population. You only have 1, 2, 3, 4, 5, 6, 7, 8, 10 people in the population. And you see the shaded part. So the probability of getting someone that scored a 5 or higher in your sample is going to be 2 out of 10 because there's only one 5 and one 6, so 5 or higher is going to be 2 out of 10, and that's a probability of 0.2. Let's look at an example here, a question. You have a deck of 52 cards. You have 12 royalty cards. Those are face cards. So those are Jack, Queen, and King. If you randomly select a card from the deck, what is the probability of obtaining a royalty card? So if you take one draw from this deck of 52 cards, and 12 cards are face cards, Jack, Queen, King, what's the probability of getting a face card? Or they call it a royalty card. Well, it's 12 possibilities, 12 outcomes that we want, 12 successes over 52 possible outcomes. So it's 12 over 52. And the answer is B. As you can see here, that's the correct answer. There's 12 possibilities. There's 52 cards. If I only draw one card from a deck, it's 12 out of 52. So this is really, really basic stuff. The chapter on probability here, it's not complicated at all. Stuff that you've learned many, many years ago. Let's look at this true-false statement. Choosing random individuals who walk by you yields a random sample. Well, I just kind of said that before when I talked about convenience sample, which is the people that are, kind of around you and you can put into your sample. So people that walk by you aren't random at all. Maybe if you go to class and you take a night class, maybe the people that walk by you are the night students. Are they representative of the entire population of BMCC students? No, because BMCC students have morning students, afternoon students, night students, and weekend students. And then you have distance learning students. So those people around you that are in your 5 o'clock class are not necessarily representative of the entire population of BMCC students. They're just the people that have 5 o'clock class. So that's a convenience sample, and therefore it's not a random sample. Because those people were not given, everybody was not given an equal chance of being in your sample if you just took people around you. Because the people that are not there, or the people that are online, never had a chance to be in your sample at all. So therefore, false, not a random sample. Statement 2, probability predicts what kind of population is likely to be obtained. Well, if you know the population, you can predict the sample. But if you know the sample, you can't predict the population. So if we look at this, they're both false. Of course, in the first scenario, it's a convenience sample, so individuals don't have an equal chance of being selected. And in statement 2, the population is given. The population predicts what a sample is likely to be, not the other way around. So if you're given a population, you can predict with a probability what the sample is going to be. But if you're given a sample, you can't predict the probability of the population parameters. You can try to draw an inference from the sample of the population, but you can't just use probability to predict what the population is. Now, when we talk about probability, there's all kinds of distributions. However, in psychology, we focus on the normal distribution. The normal distribution is a very common distribution in psychology. Mostly, almost everything except for reaction times will fit a normal distribution. Reaction times tend to be skewed. The normal distribution is that bell-shaped curve. It's symmetrical. Most of the cases are in the middle. The mean, the median, and the mode are all equivalent in one peak of the curve. And as you get away from the mean, median, and mode, you have less and less cases. The normal distribution is also defined by an equation. And we can determine the proportions that are underneath the normal distribution because we have the equation. And we need to convert this normal distribution into z-scores to then find the proportions in the areas. Here's the normal distribution equation. Y equals 1 over the square root of 2 pi sigma squared times e raised to the negative x minus mu squared over 2 sigma squared power. So that is a mess, right? So we're not doing this in this class. We're not going to basically integrate the curve. So that's what you'd have to do here. If you wanted to find the area or the proportion underneath different parts of the normal curve, you would need to do integration, which is basically calculus, second semester calculus, where you find the area underneath all kinds of, so you're given basically an equation, and then you integrate the equation, and then you can find the area between the lower interval and the upper interval of your integral. And you can even do it when you have objects in multiple dimensions. You can have multiple integrals. You can have double and triple if you're going for 2 and 3 dimensions. We're not doing that in this class. That is, to integrate this would be a mess. You can use a computer program to do it for you fairly easily. So you can do this in like MATLAB or something, or there's a bunch of other mathematics. I guess Maple. I think that stuff is free, so if you have access to it, you can do it. But there's no point unless you want to just do it for the sake of doing it. All of this stuff has been done for you by a computer, basically. And so these integrations or these areas under the curve have been put into a table called the standard normal table, which is in your appendix, Appendix B. And based on that table, you can find the areas instead of actually integrating this complicated equation. But it's nice to know that this isn't the equation for the normal distribution, where mu is the mean and sigma is the standard deviation, pi is a constant, and e is a Euler's constant. Now, we've done approximations based on the normal curve. And we know that between 0 and 1 standard deviation, so these are all z-scores here on the x-axis. So between 0 and a z-score of 1, you have 34.13% of all scores. Between 0, the mean, and a z-score of 2, you have 34 plus 13.59, which ends up being 47.72%. So you just add those two pieces, the 34.13 and the 13.59, and that gives you the area between 0 and positive 2. More extreme than positive 2, you only have 2.28% of all scores. So this could be considered percentage of scores. This can be converted to a decimal, and the decimal is the proportion of scores. Decimal is also an indication of area, right? And in psychology and statistics in general, the decimal value is a proportion, the area, but it's also known as the probability. So these percentages really are probabilities of obtaining a score that is within these boundary points. Now, if you add up all three boxes here, 34.13, 13.59, 2.28, you're going to get 50%. So the entire right half of the curve is 50%. The entire left half of the curve is 50%. And the curve is symmetrical. So whatever happens on the right is going to be the exact same thing that happens on the left. There's also a general rule that between 1 standard deviation below the mean, which is a z-score of -1, and 1 standard deviation above the mean, which is a z-score of +1, you have approximately 68% of all cases between -1 and +1. Between -2 and +2, you have approximately 95% of all cases. And between -3 and +3, which is not shown on this graph, you have approximately 99.7% of all cases. So this is the 68, 95, 99.7% rule. Between -1 and +1, approximately 68%. Between -2 and +2, approximately 95%. And between -3 and +3, approximately 99.7%. So the text doesn't talk about this, but I'm just giving you the sort of general rule of thumb that everyone uses. Now that only tells you if you have whole score z-scores. If you have z-scores that are between those integer values that I just gave you, the 0, the 1, the -1, the 2, the -2. If you have like 2.56 as your z-score, these rules aren't going to apply. That's why you need the table. Now, why do we use z-scores? Z-scores is a standardized score, and it allows you to convert any kind of raw score, no matter how it's measured, to a common z-score. So if it's normally distributed, you can use z-scores. If it's not normally distributed, you cannot use z-scores. So if your distribution is heavily skewed, z-scores are not going to allow you to use the table. You can convert things into z-scores, but those z-scores from a skewed distribution cannot be used to find the values, the probability values in the table, in Appendix B. That's why you need to have a normal distribution to use the probability values in the table. That's important. Now, the good thing is in psychology, most things are normally distributed. So for most variables, you can use these z-scores and use the table. But if something is way skewed or multimodal or severely bimodal, and it's not close to a normal distribution, then you can't use the z-table. Now the other benefit of using a normal distribution is that if your sample is bigger than 30, right? If your sample is bigger than 30, we can assume that it's going to be normally distributed. When your sample size is bigger than 30, we can assume a normal distribution. And that's part of something called the central limit theorem that we're going to get to later in the course. And that makes a big difference because it's easy to get a sample of 30. And if we get a sample of 30, we're pretty we're basically guaranteed if we use a z-score, if we assume normality, we're okay. So unless your sample is really small and highly skewed, that means the population is highly skewed, or at least you think the population is highly skewed. Unless that's the scenario, you can use z-scores. So that pretty much means in psychology, you can use z-scores for basically everything except for reaction times, which are highly skewed. So how do you analyze reaction times? Well, you can analyze them with non-parametric tests, which are beyond the scope of this course, or you can do a transformation. You can then transfer the scores that are skewed, and once you do the transformation, the transformed distribution will be normal. That's also beyond the scope of the class, but you can talk to me about anything that's beyond the scope of the class. I'll be happy to talk about it. But for this class, the general knowledge base of this class, I'm trying to keep it very simple. This material is the simplest material that I've ever seen. And it's kind of good that it's this way because of the whole online nature of the course. If I was teaching this course in a face-to-face environment in class, it would probably be much more complex. But for online, it's a difficult situation, so the material is really basic. So for those, some of you are saying, wow, this is a lot easier than I thought. Well, it is. So for those of you that are saying, wow, this is still hard, this is tricky, it is. So it's kind of both, right? It is tricky because it's a different way of thinking about the world, but it is also easier than a lot of more advanced or upper level stats courses, at least so far. So it's a little bit of both. So hang in there. If it's difficult, if it seems like it's so easy to you, don't be overconfident because you're going to make mistakes. If you want to know more information about something, send me an email. I'll give you tons of other stuff to read. And therefore, it won't be super easy to you. Here's an example of a normal distribution with a mean of 500 and a standard deviation of 100. So if you have a score of 700, you have a z-score of 2. And we can convert all scores into the common metric of z-scores, the standardized scores. So it's always x minus mu over sigma. 700 minus 500 over 100 is 200 over 100 is 2. And then with the z-score of 2, then I can find that tail, the shaded part of the distribution, which is all scores greater than 700. I can find the probability of getting a score greater than 700 by looking in the table with a z-score of 2. And if I look up 2 in the table and I look in the tail, in the chart part that says tail, I can then find the probability of getting a score greater than 700 if our data is normally distributed, which is the example here. And we already determined this, right? We showed it to be 2.28% in the previous slide that I showed you with the z-scores of 0, 1, and 2. That tail is 2.28%, so the probability is 0.0228, which is a very small probability. So it's very unlikely you're going to have select one person with a score greater than 700 out of this sample, out of this population, I should say. And as I mentioned before, all the z-scores are in the table, which is in Appendix B. And it's called the unit normal table. I call it the standard normal table. The unit normal table just means that the standard deviation is 1. That's a unit. And it's a normal distribution. So whether you call it the standard normal table, the unit normal table, it's the same thing. That table is going to be important to you in this chapter. Here's what the table looks like. You see it ranges from a z of 0, and it goes all the way up, I think, to positive 3. And it goes in every possible interval. Now, there are no negative values in the table because whatever the positive values are, since the curve is symmetric, the negative values are the same. So you don't need negative values because they're the same as the positive values. Now, if you look at the first example, where it says B here, the top picture, if the larger part of the curve is shaded, like here we're looking for everything less than Z. Since Z is positive, everything less than Z is going to be a larger part of the curve. The larger part of the curve is called the body. And so B here, the B column is the body. That's the larger part of the curve. The smaller part of the curve, if you look at the second picture, is called C, the tail. See how in the second picture that C is smaller than the rest of the curve? The rest of the curve is B, and C is the tail. So C is always the tail, B is always the body. The body is always bigger than the tail, always. And then we have D. D is the area between the z-score and the mean. So you have 3 columns here: B, the body, C, the tail, and D, the area between the z-score and the mean. Column A is just your z values. So you need to practice using the table in Appendix B. So here's another example of the body and the tail. So if your z-score on the left is positive 0.25, the body is going to be the area that's less than that value, because that's the bigger area. So if your z-score is positive, the body is going to be the area to the left. If your z-score is negative, the body is going to be the area to the right. Look at figure B. If the z-score is negative, the body is the area to the right. If the z-score is positive, the body is the area to the left. Now, the one thing about the body is it's the same. So whether your z-score is 0.25 or negative 0.25, the body is going to be the same. And then the tail is going to be the same. The tail is going to be the rest of the curve. So if your z-score is positive, the tail is to the right. If your z-score is negative, the tail is the area to the left. And of course, they're the same because the z-scores are the same. Right? 0.25, whether it's positive or negative, gives you the same values. It just means whether the z-score is on the left or the right side of the mean. And then the area in the middle where you see 0 and you see the z-score, that little area between 0 and the negative 25 or between 0 and the positive 0.25, that area is D, the score between the mean and Z. That little strip is D. So B is the body, C is the tail, and D is the area between 0, which is the mean, and the z-score. That little strip between 0 and the z-score of negative 0.25 or positive 0.25. If you know the z-score, you can look up the corresponding proportion. You can look up the proportion that's in the tail, in the body, or between the z-score and the mean. Those are your three options. If you know the proportion, you can look the proportion up in the table and then find the z-score. So that's a reverse lookup. You look up the proportion in the table, and then you find the z-score by scrolling to the left into column A. Probability is the same thing as proportion. It's a decimal. We express probability in decimal form. It's also the same thing as the area. So the entire curve has a area of 1, or represents the probability of 1, right? 1 means that you're guaranteed to have some value under the curve. That's all it means, is you're guaranteed one of those values. That's under the normal curve. That's why all those values sum to 1. The area of the curve is 1. So probability is always expressed as a proportion, not as a percentage. If I ask you for percentile rank, I want a percentage. If I ask you for probability, I want it as a decimal, a proportion. The decimal must be between 0 and positive 1. There are no negative probabilities, ever. Just like there's no negative percentages, and there's no negative areas. They're always positive, or 0. So here's 3 different examples. In the example A, you're asked to find what is the probability of getting a z-score greater than 1. That means it's to the right of that 1, so that's the tail. So you would look up the tail for 1 as a z-score. For example B, what's the probability of getting a score that's less than a z-score of 1.5? So less than means everything to the left. So you would look up 1.5 in the table and then look up body, which would be everything to the left. And in C, if you want to find what the area is less than, what's the probability of getting a z-score less than negative 0.5, you would look up negative 0.5 in the table, but you would also look up tail, which is everything to the left. So those are 3 possible scenarios, and there's many more. You just need to know, are you looking at body? Are you looking at tail? Are you looking at mean to z? And that depends on whether the z-score is negative, positive, and what the actual parameters that I'm asking for in the problem. So find the proportion of the normal curve that corresponds to a z is greater than 150. Well, to find this, you're going to look up 150 in the table under column A. You would find 1.50 as your z-score. And if I want greater than 1.50, I want everything to the right. Since 1.50 is to the right of the mean, and I want everything to the right of 1.50, I want the tail, which is column C. So here I would look up 1.50, and I'd look up column C to find the tail. And that value is going to be really small. So if you look at A and B, those are more than half the curve in A. B is exactly half the curve. Obviously, that's impossible. C is almost half the curve. Obviously, that's not going to work. So you're already left with one option, which is D, which is about 6% of the curve, or a probability of 0.0668. And the answer, of course, is D, because everything to the right of 1.5, there's not much left of the curve, so that's greater than 1.5. So if you're not sure what's going on, draw the curve. I like to draw the curve and then draw a line straight down where the z-score is. I also like to draw the mean in the middle. That helps me. I put the mean of 0 in the middle of the curve, and then I draw a line at 1.50, and then shade everything to the right of 1.50. And that is area C, and then find C in the table. And you'll get the answer of 0.0668. So here's another true-false. For any negative z-score, the tail will be on the right-hand side. Well, obviously no, because if it's a negative z-score, it's to the left of the mean. And if it's to the left of the mean, the tail is going to be on the left side, and the body is going to be on the right side. And for question 2, if you know the probability, you can find the corresponding z-score. Well, it depends, right? Because you can know the probability, but the probability could be on the left-hand side of the curve, or it could be on the right-hand side of the curve. So if you know for example, if you know the probability is 0.1000 or 10%, well, how do I know that that probability corresponds to 10% of the bottom of the scores or 10% of the top of the scores? So it could be on both sides of the curve. So just knowing the probability doesn't tell you whether it's a positive or a negative z-score. So obviously you need more information. So obviously the first one is false. And the second one is you find the proportion in the appropriate column and then read the z-score. But you also need to know if you're looking at the top 10% or the bottom 10%. So that's kind of a could be not. Now, on the exams and stuff, or in the problems in the text, they will specify. So they'll say the top 10% or the bottom 10%. So you need more information than just 10%. You need to know if it's top or bottom. Right. Or they'll ask you, like, what is the percentage between 2 points? And that way you can find the two z-scores that demarcate like the middle 50% of the distribution. That's very easy to find. So there needs to be a little more detail given, but if you know the proportions, you can look up the proportions in the table and then determine what the z-score is if you're given those instructions. Now the table, as I mentioned before, only specifies probabilities for normal distributions. So if you don't have a normal distribution, you can't use the table. So what you have to do is transform your raw scores into z-scores, and then look up those z-scores in the table and get the corresponding proportions. And that will give you proportions or probabilities, the answers to the items that you're being asked for. If you look at IQ scores, we know the mean IQ is 100 and the standard deviation is 15. So if I want to find what proportion or what's the probability, same question, what's the probability of selecting someone from a normal distribution that has an IQ less than 120? So I can find the z-score from 120. So it's going to be z is going to be equal to 120 minus 100 over 15, which gives me 20 over 15, which gives me 1.33 positive. So my z-score for 120 is 1.33 positive. If I want all scores, or the probability of selecting a score that is less than that particular z-score, I need to look up 1.33 in the table under z, which is column A, and then I need to look at the body, because that's the larger portion. So everything to the left. And that will give me the probability by looking up 1.33 and then looking at the body column, which is column B. If I wanted to find the area between two scores, it's a little bit different here. So let's say I wanted to find the probability of getting a item or a person that's between a score of 55 and 65 on whatever metric you're looking at. And I know that the mean of the population is 58, and the standard deviation is 10, and I'm assuming that the population is normally distributed. So if that's the case, and I'm dealing with a normal distribution of the population, I need to find two z-scores. I need to find the z-score for 55, and I need to find the z-score for 65. Well, I can do that easily just using the z formula. So for 55, it's going to be z is 55 minus 58 over 10, which is going to give me negative 3 over 10, which is negative 0.30 as my z-score. And for 65, I just plug in 65 minus 58, which is 7, over 10, which gives me a z-score of positive 70. Now, if I want to find the area between those two z-scores, negative 0.30 and positive 0.70, I can look at column D, the mean to z. So do the column D for negative 0.30, and that will give you that small slice between negative 0.30 and 0. And then look up column D for 0.70, and that will give you that little bit larger slice between 0 and 0.70. And once I find those two slices, I add them together, and that'll give me the probability of getting a value between those two scores. So it's simple as adding D for negative 0.30, and then D for 0.70, add those two values together, you get the probability. Not difficult. If I'm doing another example here where I'm looking between 65 and 75, I convert those two scores to z-scores once again. So that gives me 0.70 for a z-score for 65, and it gives me 1.70 for a z-score for 75. And then I need to then find that area between. So here, since they're on the same side of the curve, they're both on the right side of the curve here, I could do D, column D for 1.70, and do column D for 0.70, and they overlap, right? So the column D for 1.70 is going to be larger than the column D for 0.70. So what I have to do is, since they overlap, subtract biggest minus smallest. So I do column D for a 1.70 minus column D for 0.70, and that gives me the area in between them. Now you always have to do the bigger area minus a smaller area, because otherwise you'll get a negative number. And a negative number is impossible. So you cannot have a negative value. So if you do 0.70 minus 1.70, do the d values, you're going to get a negative value. So you know that's incorrect. You always have to do the largest part minus the smaller part to get the part in between. You must have a positive value. So this figure just shows you the different ways we can find the probability, the z-score, and the raw score. So if you have a raw score, you can convert to z-scores. So you can get the z-score, and then based on the z-score, you can get the probabilities. That's one way to do it. Start with a raw score, convert to a z-score, and then convert to a probability. If we have the probability, we can convert to a z-score, and then convert that z-score back to a raw score. So that's another way we can do it. We cannot go directly between a raw score x and a probability. You can't do that. You must always work through z-scores. You cannot just go from raw score to probability. You must convert everything to z-score first and then to probability. Or convert probability to z-score and then to raw score. And that's what this picture is showing. So here's another example where we're looking for the top 10% of all scores in this distribution. So if the mean of the distribution is 24.3 and the standard deviation is 10, and I want the top 10%, that's my proportion. So 10% is 0.1000. And I want that shaded area to the right. That's the tail. So that's going to be column C, the tail. So I need to find a z-score for that tail. Once I look up 0.1000 in column C, which is the tail, that will give me the z-score that I'm looking for. And that z-score is 1.28. So a z-score of 1.28 has 10%, or if you write that as a proportion, 0.1000 in the tail. Now that I have the z-score of 1.28 that corresponds to the top 10%, I can convert that 1.28 to a raw score. And all I have to do is take z, multiply by sigma, So 1.28 times 10, the standard deviation, that gives me 12.8, and then add it to the mean. 12.8 plus 24.3 gives me 37.1, and that's my raw score. So once I have that z-score, I do z times sigma plus mu to give me the raw score. And when I compute that, I get 37.1. So here's an example where you're doing it backwards. You're starting with a proportion. You're looking up that proportion. Since this is the tail, I'm looking up that proportion in column C, which corresponds to tail. Once I look up the proportion in column C that corresponds to tail, I can then convert that to a z-score based on the table. So I go from column C, find 0.1000, or whatever's closest to that value. You're not going to always find the exact value in the table. So pick the value that is closest to the actual value you're looking for. Once I take that closest value, I then move across to column A and find the z-score that corresponds to that value. In this case, it's 1.28. Once I find that z-score, I then can convert to the raw score. And I've done the problem backwards. So forward or backwards, it's the same process, just done a slightly differently. If I'm trying to find the middle 90%, what I need to do is I need to look for 45% in column D. Because remember that column D is from the mean to the z-score. So column D on the right has to be 45%, and column D on the left has to be 45%, because it's symmetrical, right? So whatever's on the right has to be equivalent to whatever's on the left. So if I find 45% on the right, I'm going to automatically find 45% on the left in terms of z-scores. Because one z-score will be positive, the exact same z-score will be negative on the other side. So if I look up 45% in column D, which is mean to z, I find a z-score of 1.65. So this 1.65 corresponds to a column D value of 45%, which as a decimal is 0.4500. If I look that up, I get a z-score of 1.65. So that's in column D, mean to z. So you want to look up 45% as a decimal in column D. That gives you a z value of 1.65. Now, it's very easy to find the other z value because it's symmetrical. So if it's 45% on the right, it has to be 45% on the left, which gives me negative 1.65. So they're just mirror images. We'll just change the sign. Once I have those two z-scores, I can then convert to raw scores by using the same formula I did in the previous example. So z times sigma plus mu. So 1.65 times 10 plus 24.3 gives me 40.8. Negative 1.65 times 10 plus 24.3, so that gives me a negative value. That gives me negative 16, plus 24.3 gives me positive 7.8. And those are my two raw scores. So here you're looking at column D. You're finding the 45% in column D. You're getting the z-scores, which are the exact same value but different signs. And then you're converting those two z-scores into raw scores. And that'll give you the raw scores where you're having 90% in the middle. Now, percentile rank is just the same way as saying everything to the left of a particular z-score. So before we did what percentage is lower, the same or equal to a particular z-score, and we looked up either the main part of the distribution or the tail. So the body or the tail, depending on if it's positive or negative. That's what we're doing with percentile rank. We're finding the percentage of all scores that are less than or equal to a specific score. For example, if you had a percentile rank of 90 on the stats exam, that means 90% of the entire class scored the same as you scored or worse or less on the exam. That means you did really well if 90% of people scored the same or less than you did. So you can reframe a lot of these questions as percentile rank. So percentile rank basically means look to the left of the z-score. That's what it means. Look to the left of the z-score and find the area, find the probability. So this example involves Mensa, which is basically the really, really high IQ group that's out there. So you require an IQ score of 130. The IQ score has a mean of 100 and a standard deviation of 15. So what proportion of the population is going to be in Mensa? So I need to find the z-score first. So if Mensa is 130, it becomes 130 minus 100 divided by 15. And that gives me 30 over 15, which gives me a z-score of positive 2. Now I want everybody to the right of positive 2 because I only want people that are 130 and above. So if I find positive 2 in the table, which is to the right of the mean, obviously it's positive, I need to look at the tail. And if I look at the tail, which is column C, I then find 0.0228 as my answer. So that means there's only a probability of 0.02 for people to be in Mensa if I randomly select someone from the population. It's like a 2% chance. So it's a pretty rare group. And that's what the answer is, 0.0228. So that was basically find the z-score and then look in the tail because I want everything to the right. It's a positive z-score, so the tail is everything to the right of that value, which is 0.0228 once I look up 2 in column C. True or false? It's possible to find the x-score corresponding to a percentile rank in a normal distribution. Well, you can find that. Once you get the percentile rank, you need to convert to a z-score, and then you convert to a raw score. If you know a z-score, you can find the probability of obtaining the z-score in a distribution of any shape. No. You can only find probabilities that correspond to z-scores when you have a normal distribution. So if your distribution is not normal, you can find z-scores, but you cannot find the probability of getting those z-scores. So obviously that's false. And that's what we got here. So the first one we can transform. Percentile rank gets transformed to z-score, which then gets transformed to raw score. And obviously you need a normal distribution to use the probabilities that are given in the standard unit table or standard normal table. If you're doing research, you generally begin with a normal distribution, and then if you take a sample from that distribution and you give it a treatment. So if I take a sample from a normal distribution and I give that sample some kind of treatment, I can then see if the treatment works. Because obviously if I give that sample a treatment, the mean of that sample should be different than the mean of the population. Because nothing happened in the population. We didn't treat the population. So I want to see if the sample is different in terms of mean, or whatever I'm measuring, after I give the treatment. So I can find the mean of the sample compared to the mean of the population and determine, is this sample the same as the population, or is it different enough from the population to say that the treatment worked? So if the treatment doesn't work, the mean of the sample and the mean of the population will be basically the same. They're not going to be exactly the same because you'll have, you could have sampling error, right? But if the treatment does work, the mean of the sample should be substantially different from the mean of the population. So let's say the population has a mean of 400, it's normally distributed, and the standard deviation is 20. I then take a sample from that population. I give that sample some particular treatment. I hope that that sample now has a mean that is a lot different than 400. If my treated sample has a mean of 400 or close to 400, then guess what? The treatment didn't work because there's no difference now, right? The sample basically is around 400 because the treatment didn't do anything. And you took the sample from a population that had a mean of 400. So if that sample after treatment is close to having a mean of 400, then guess what? Your experiment or your research did not work. Your hypothesis is not successful, right? You don't support it. If, however, that sample that I treat is different, significantly different, that means much different from 400, then I can conclude that the treatment does work. The farther away the mean of that sample is to 400, the more likely that the treatment worked. So if that sample is 450 and the standard deviation is relatively small, then it's probably different, right? The treatment did work. If that sample is 410, then it's not big enough, right? So it depends on your standard deviation and your sample size as to how far apart the mean has to be. But I would hope that that sample would have a z-score that is pretty far away from 0, if we're looking at z-scores. I'd want the z-score of that sample that gets the treatment to be far away from 0. The farther it is away, so I would say definitely past 2 or -2. I would hope that it's even further past that. I want it to be past, there's a special cutoff value where we can say that the sample is different based on its z-score. And that cutoff value is 1.96. So it's around 2. So if my sample mean that gets the treatment has a z-score that is greater than 1.96 or smaller than, more extreme than, -1.96, then I can say that the treatment works because the sample mean is much different than the population mean. In other words, that there's a 95% chance if my sample mean has a z-score of greater than 1.96 or less than -1.96, there's a 95% chance that my sample is different than the population mean, and therefore the treatment was successful. So it's very unlikely that the sample, after getting the treatment, belongs to a population that has a mean of 400. There's only a 5% chance that this would be a random sample from a population with a mean of 400. And if there's only a 5% chance of that happening, we say that that's very unlikely. So that therefore our sample does not come from this population. It comes from some alternative population where the mean is greater than 400 or less than 400. So the treatment works. And we call this statistically significant, which means that this sample, the difference between the sample mean and the population mean is not due to chance. It's not due to sampling error. It's not due to the fact that you just randomly chose a sample from a population. It's not due to that. It's not just due to the regular differences we get when we take samples from a population with a mean of 400. So it's not due to sampling error. It's not due to chance. It's due instead to the treatment, which we call the independent variable. So this is really important, and this is going to get fleshed out over and over again in the upcoming chapters. If your sample, after getting a treatment, is much different than the population, and it has an extreme z-score of greater than 1.96 or less than -1.96, we say that we have a statistically significant difference, which means that that sample is not likely, to come from that population, which means that the treatment actually did something. And that is the goal of all research. The further away our sample is after treatment from the population that does not get the treatment, which is generally represented by what is called the null hypothesis, the further away our sample is from that population of nothing happened, right, the more effective our treatment is, and the more likely we can then say that our hypothesis should be supported. We cannot prove anything, but we can support our hypothesis, which is the goal of all research. Now, that doesn't mean you're 100% right. There's still, in this case, there's a 5% chance that, with a z-score of 1.96, there's still a 5% chance that our sample really is no different than the mean of 400 here. There's still a 5% chance of that happening for it to be a random sample from this population with a mean of 400, which basically means there's a 5% chance of sampling error. Now that's small, so we're willing to live with that. We're willing to live with that 5% error rate. However, that is an error rate. And there's always going to be a chance that you make an error when you say that your sample is different from the population. We have to determine what value are we okay with. What's the chance that what's the chance we're allowed to give ourselves to make that mistake? And in most of the cases, 5% is okay. We're willing to live with a 5% chance we've made a mistake. Now, if it's 10%, that's too much of a chance we're making a mistake. We want it to be less than 5%. And that's going to correspond to what is known as the alpha value, when we get to type 1 error, and we get to hypothesis testing. We're always willing to live with a 5% type 1 error rate when we test our hypothesis, which means that we're never 100%. We could be 99%. You want to make this 1%? We could make a 1% error rate. The problem with making it really small, the error rate, is a lot of times if we make the acceptable error rate too small, we miss out on hypotheses that really are different, right? So we're being overly restrictive, and then when there is an effect of the independent variable, we're not going to find it. And then we end up with a study that's underpowered. And we end up with something called type 2 error. So we're going to get to type 1 and type 2 error and how to balance it out. But this is a good introductory concept of we want our sample mean to be as extreme as possible from the population mean that does not get treatment. And if our z-score is big enough, then we can say that the treatment actually worked in the sample, compared to the population, which represents no treatment. And that's kind of the stepping stone for things that are going to happen later in the course. So hopefully that kind of makes sense, and you get it in this whole chapter on probability, which is mainly a chapter on z-score and using the table. There's not as much probability. It's very basic probability. There's a lot of other probability concepts that I'm not going to go over right now. I just want you to understand mainly the z-score stuff. So that's it for chapter 6. Hopefully that made sense and this is helpful. Bye for now and see you next chapter.